Hi everyone. Today we are going to solve another problem that is generally asked in machine learning system design interviews. That is YouTube video search. Before jumping into the video, I would like to cover what I'm going to cover in this video. So the first thing would be the objective, that what are we going to build. Second is the input and output to the system. Third is the data engineering part, where I'm going to tell that what data do we have exactly. Fourth is the feature engineering part, where we are going to convert this data into features which the model can understand. Fifth is model development, where I'm going to tell you that what kind of model we are going to use to solve such a problem. Sixth would be the evaluation part, where I'm going to tell you that how do we evaluate the model once it's built. And seventh would be the serving part. The serving would be the last part, where how do we serve it to the end users. So start with the video. The first part is objective. See, the objective is something like whenever you go on YouTube and write a textual query on the search bar and the videos comes up, we are going to build the same system. Okay, here we are giving some constraints to it, that only textual query is allowed. Second constraint is that only we are considering that the language is currently English. And to be sure, we are making one more thing, that it's not like personal recommendations. So for example, if a user sitting in Bangalore searches for cute dog videos, he or she should get the same videos as a person who is searching for the same in US or a different user. So it's like for every person who is searching the same stuff should be recommended the same set of videos. Okay, and currently we also have this constraint that we have the data available with us, where we have that, okay, for a particular text query, let's say for a text query like cute dog video, what videos did the user actually watch? We already have this data present with us, but how to take care of this data and to convert this into features is something which we need to solve. Okay, now let's consider that we have around 10 million videos with us. Okay, so these are some of the constraints that we are currently we have taken. Okay, now coming to the second part, that is input and output to the system. See, as I said, that the input would be just a textual query. The textual query would be just a cute dog video. And output would be, let's consider this is a YouTube video search service system that we made. The output is a list of videos which are relevant to this particular topic, and the video at the top should be the most relevant one. We need to make this sure, most relevant. Okay, now coming to the third part, that what data do we have? So as I said, that we already have this annotated data, where we know that, hey, for a particular video, let's say cute dog, for a particular video, let's call this video XYZ, what text was written or what query was given. So let's consider this query as cute dog videos. Okay, and whether the user clicked it or not. So if the user clicked it, it's 1, whether it was just an impression or not. So it is possible that let's say there were 10 videos that were recommended. The user scrolled all of them but only watched the 5th one. So on the 5th one, we would have something like it was clicked, and it had an impression of 1. But for all the videos which are not clicked, it will still have an impression of 1 because the user scrolled through them. but the clicked would be 0. So we have such kind of data where we have a video ID, what query did the user write, whether it was clicked or not, and what was the impression. Okay, now we need to somehow convert this data into features. Okay, now for that, let's jump onto the feature engineering part. So see what exactly the video will hold. So video will have like information like title, description, plus the video itself, right? And we know that somehow, let's say this is text. Okay, now this text plus this is query text, and this is the whole video. Now let's say if I try to because again my model won't be able to understand either the English or either the video or anything like that. We need to convert them into numbers. Converting them numbers is a task which we need to understand how we are going to do that. But let's say we somehow were able to convert them into numbers, right? Let's say this textual query was numbered something like 0.6, just a vector, 0.8, 0.4, something like that. This is just a 3D vector. Similarly, let's say this video is also a 3D vector, 0.8, 0.5, 0.6. Let's say if we do a dot product of them, okay, and if both of the dot, when we do the dot product and the score comes high, then it means that these both are closer to each other, right? So, and what do we want exactly is that all the videos which are related to a particular topic should be closer to each other, right? So for example, if I search videos about dog, so they should, all the videos somehow should be closer to each other. For example, if a particular video could be represented using a number, just a single number. So let's say it is represented using 16.1. Okay, and there is another dog video, so it should be represented by 16.15, something like that. We want something which makes sure that all the videos which are related to each other should be closer to each other, so that whenever we are trying to find a text which is related to one, we could be recommended the other things as well, right? So this is the problem that we need to solve. So for that, first we need to think that, okay, how do we take care of this query text? Let's try to solve this problem first. So see, query text would be just a sentence, right? But sentence wouldn't hold any meaning. But we need to take out the meaning of the sentence. So if I say that cute dog videos, it means that we are trying to search videos that are related to cute dogs, right? But we need to understand the context, the semantic meaning of this sentence. So for that we need some model which could convert them into a vector of numbers which will represent the semantic meaning of that. So for that, rather than we train a model, we already can use a pre-trained model for that. Example, but or sentence but. These are just pre-trained models that are given by Google. There are some pre-trained models given by OpenAI as well. We can use them, and what we can do is that we can simply convert this whole sentence into a vector, into an embedding, and what does this mean? That this particular vector will represent the whole sentence, right? Now, just going beyond scope of this video, like if you generally want to understand that, hey, how does this query text even gets converted into this kind of embedding space? So the answer is transformers. Like bird, sentence, bird, all of them internally uses transformers. So see, transformers generally has a very small architecture. Like I can just cover the architecture here. It's just beyond the scope of the video. You can skip this part if you don't want to understand this part. But generally what happens is that in these kind of pre-trained models, so let's say there's a sentence, my name is Jatin. So basically every particular the whole sentence is first converted into tokens. Okay, and these tokens are then converted into embeddings. Embeddings are just vectors. Just let's say a particular token, let's say my, it's converted into 0.1 to 0.15, some particular embedding. Okay, then we apply positional encoding to it. Position encoding to understand that why did my, like to understand like, okay, my come first, then comes name, then comes is, and then comes my name, Jatin, right? Then we send it to a transformer based block, encoder based block, where initially we have self attention. This is generally multi-head self attention. Then we have add and norm. Then we have a feed for a neural network. Then again add and norm. So see, everything has its own like reason of being there. I don't want to go in the depth of a transformer, but generally what happens is that once you give this a particular token, what will come out is a token, embedding, which has the semantic meaning of that word, right? And once we get it for all the words, my name is Jatin, we can apply max pooling or mean pooling. We can apply mean pooling to get the average of all the embeddings that we get, right? So basically we will be able to understand like what is the sentence wanted to say, like we will be able to capture the semantic meaning of the sentence. So for this we would simply go with a pre-trained model like BERT or sentence BERT, and eventually convert this into a embedding or a vector which holds the semantic meaning of it. Okay, so we were able to solve this problem of query text. Now we need to solve this another problem, that is we have a video. Okay, now video has like two things here: the video itself and then we have the title plus description. See, title plus description is again just text, right? So for them again we can use a model like BERT or sentence BERT, where we could just pass it directly and convert them into a single embedding. So this embedding would contain the semantic meaning. Okay, but like how do we take care of this video? Because video also we need to truly understand what the video actually captures. Now there are two things to it. First thing is that there are like, rather than training a model for going through every video and converting them into a embedding, the simplest thing could be just take a pre-trained model. Now actually there are two types of model here. One is a video level encoder or a frame level encoder. See, the thing is that what this type of model will do is that they will take the whole video and convert them into a embedding, and they will capture all the motions in the video and try to understand everything in the video, and then it will give a proper vector to you. But the problem with these kind of models is that they require high compute. They require very high compute. Okay, so and even if you take a pre-trained model as well, then also it would be expensive for you, because the thing is that we need the embeddings in the fastest way possible, right? So rather than going with these models, we generally go with the frame level encoder models. Why? What we can do is that, let's say this is our video, it's like 10 seconds long, so we can divide them into like 8 to 10 frames, and we can pass it to pre-trained models like clip, where clip gives a it's just a pre-trained model which gives the semantic meaning for every frame or every image that it gets. Okay, and let's say for 10 frames it gets 10 embeddings. So what we can do with that, we can just aggregate them, means just take a mean of them. So basically the last vector that we will get will hold the whole semantic meaning of that video, right? And it's not that too expensive as well, and easy to maintain as well. So we would go with such model, that is a frame level encoder. Okay, but here if you understand, the only thing we did was whatever text we had, we converted into a text embedding, and whatever video we had, we converted into text embedding plus video embedding. Now somehow we need to make sure that these two things, like this text encoding of this plus video embedding of this, is turned, let's say we have a single embedding, somehow we have a single embedding. When we concatenate them, let's say we have a single embedding somehow. So all these videos which are similar to each other should be closer to each other. Okay, this is something which we need to reach towards. Okay, so for that particular part, how we are going to solve that problem, let's see that. Coming to the model development part. See, what exactly is our end goal? Our end goal is that the videos which are similar to each other should be closer in the embedding space. So basically, let's say this is the embedding space for dog videos. So all the dog videos should be quite closer to each other. This is the end goal that we want to reach. So if we want to attain such a goal, so generally what kind of models we use is, or what kind of learning we go for is contrastive learning. Now, what does this mean? And what exactly happens in this kind of learning? Coming to the part that what is contrastive learning. So in contrastive learning, what happens is that, let's say we have a video and these are our queries. Okay, so we will have like n number of queries here. Okay, and what eventually will happen is that only one positive query will be there, and n minus 1 negative queries will be there, means which are not related to the videos. For example, here the video is related to cute dogs. Okay, so first query could be cute dog videos. The second query could be Ben 10 videos. Third query could be Punjabi songs, all that stuff. Okay, now what eventually happens is that once we train our model, these video embeddings gets updated. Now how do they get updated? I'll come to that, what exactly gets updated in the model. But these video embeddings gets updated, and all the video embeddings which are similar to each other comes closer. Okay, now the thing is that, let me just give you an example that how eventually the model works. See, let's call this embedding as V1, and let's call these query embeddings as, for this E1, this one E2, E3, and so on. And what we are going to do is that we are going to do a dot product. So it would be E1 V1, E2 V1, E3 V1, En V1. For this particular sample, we know that the label would be 1, means the user clicked it. And for others, it will be 0. So eventually, we need such a loss function which helps us in the classification of 1 or 0, right? That is one thing. So now another question comes that what exactly loss function we will use. Second, okay, let me write all these questions down. What exactly do we train? Because the first question that you would think is that, okay, we are just getting the embeddings from pre-trained models. Why we need to train anything? Okay, I'll tell you the solution for it. Second is that, hey, like what will be the exact loss function? And okay, I'll just cover these two questions first and we'll move along. So what exactly do we train? I'll just start from the scratch of the training part. See, what did we have? We have this video embedding, which had this text embedding from the title per description, and then we have this video embedding. Now, do we concatenate it directly? The answer is no. Generally, what happens, like for a production-based model, how it works is that we use something called weighted sum. Okay, now what does this mean? So let's say you have title per description. You pass it to a pre-trained model like BERT. It gave you a 256 dim vector, which hold the semantic meaning of this title per description. Then you have this video. You passed it to a pre-trained model like clip. It gave you a 256 dim vector. You have these two vectors. Now to get a final vector, you would use something as weighted sum. Now let's say this particular vector is named as t. This particular vector is named as v. Okay. So how do we apply this weighted sum? Alpha dot t plus 1 minus alpha into v. Now why are we even applying that? See, here alpha means that how much importance do you want to give to the title per description. Let's say if I keep this alpha as 0.8, it means that 80% of the importance needs to go to this title per description and rest 20% would go to the video embedding part. Because here we are generally seeing that, hey, if we are searching about cute dog videos and in the title, if it's written cute and it's written dog, then it certainly means that the video should be at the top of the recommendation that we are doing, right? So for this, we would go something like this weighted sum, and we get a final video embedding. Okay, let's say we get this. Now, what are we going to do with this? See, this final video embedding would be passed through a projection layer. Okay, and converted into a different embedding. Now, this particular projection layer has a weight WV. This is a weight matrix. This exactly gets trained. Okay, so this is the part that we are training into. We are training for. And similarly, you had your query, right? So for query, what you are going to do? Pass it to a text encoder. But again, we need to pass it to a projection layer. Let's say the weight of that layer is WQ. And this WQ, when gets multiplied with this embedding, then it gives the final query embedding. Okay. Now, what eventually happens? We have final video embedding. We have final query embedding. And then we have something like either it has to be 1 or either it has to be 0. Either the user clicked it or either the user did not click it. Okay, so what loss function we would go for? This is called as, and the loss function that is used is softmax contrastive loss. Now, what does that mean? Like, how does the loss function even look like? So the loss function would be minus of log e raised to power query into video by summation of all exponent e raised to power q dot v for all the samples. Now, for example, let's say we had 3 samples. Okay, 1 positive, 2 negative. We did for this, we calculated the query embedding, we calculated the video embedding, we did a dot product, we got the score 0.8. For this, we got the score as 0.4, we got the score as 0.8. Okay, we did e raised to power 0.8, e raised to power 0.4, e raised to power 0.8 again. Okay, then the formula would be hyphen e log. Let's call this quantity as 1.15, 1.12, 1.14. So the score, 15 only. So it would be minus of log 1.15 by 1.15 plus 1.12 plus 1.15. So let's say if the loss comes out to be high, let's say it comes out to be 0.9 or 0.8. So what eventually it means? That means that these embeddings are currently closer. The positive embeddings is closer to the negative embeddings. We need to pull them apart. So eventually what will happen is that my model will re-update these weights, WQ and WV. It will re-update these weights to put them far apart. So the videos which are similar to each other will be pulled closer, and the videos which are far away from each other, which are not similar, will be put far. So this is how exactly the model training part is covered. Right. Now, coming to the part that how we are even going to evaluate this model. See, for evaluation, there are 2 things. First is offline evaluation. Second is online evaluation. Now, what does this offline evaluation mean? Offline evaluation means that you already had your historical data, and currently, let's say you have trained the model, but you are not making it live. You just want to make sure based on the historical data whether my model even works fine or not. And online means that you are serving it to the whole community now. Like, so you made the model live and you are giving to some percentage of users to make sure that, hey, whether my model is working quite expectedly or not. And there are some evaluation techniques for checking that. We will cover the first ones which are easier. That is the online evaluation part. See, let's say you have made the model live. Now you want to know that whether your model is working fine or like, is it good or not. So the first metric that you can use is click-through rate. Now, what does this click-through rate mean? Click-through rate means that let's say the user search something. Okay, so total number of videos he or she clicked by total number of impressions. So let's say if this is high, it generally means that the videos which you are showing are at least good. So that's why the user is clicking them. Second is number of watch hours on the topic searched. So let's say you trained this model and made it live, and previously whenever the user used to click on videos, he used to watch it for only 10 minutes. Okay, but now when you trained the model, your model showed only relevant videos. The total time he would spend on the platform for watching such videos would increase, right? So if that happens, it means your model is good. Okay, and now coming to the part that how do we measure the offline evaluation, which is quite important. See, or offline evaluation, there are two things that are, first, how do you measure the ranking quality? So here ranking quality means that, let's say if I am searching about cute dog videos, and then at the top there is a video that is recommended where dogs are fighting with each other, that is not cute, right? So we need to make sure the relevant videos are shown at the top. It should be recommended at the top 1, 2, 3, 4, that kind of positions. So for that we have a matrix called as NDCG at the rate K. Now what does this mean? Normalized, discounted, normalized discounted cumulative gain, discounted cumulative gain. See, what is the exact formula and what does it tells? See, this parameter is specifically for measuring your ranking quality. Now, how does it measure the ranking quality? I'll give you an example to explain. So the formula is NDCG at the rate K is equal to DCG at the rate K by IDCG at the rate K. Okay, this I means ideal discounted cumulative gain. So let's say there is this model. Let's say the user watched 4 videos. Let's say user watched 3 videos. User searched about cute dog videos. He watched 3 videos: A, B, C, D. We have this data with us. He watched completely. Clicked plus watched completely. B, clicked plus watched for half of the time. Let's say the video was 10 minutes long, he watched for 5 minutes. C, clicked plus watched for 10 seconds. D, did not click. Now comes my model. Okay. Now my model said that my model showcased that for cute dog videos, my model said B is at the top, then comes C, then comes A, then comes D. Okay, rank 1, 2, 3, 4. So this is what my model told, that B should come at the top, then comes C, then comes A, then comes D. But according to you, what should be the ideal case? This should have the most relevance, right? So let's assign it a score that it has a relevance score of 3. B should be the second relevant. Let's assign it a score of 2. C should have a less relevance than this. Let's assign it a score of 1. And then assign it 0 because the user did not watch it. So accordingly, the score comes out. If we write the scores here, the score should be something like 2, 1, 3, 0. Now how do you calculate DCG? DCG at the rate K. So for here, DCG at the rate K would be DCG at the rate 4. So it means relevance of I by log of 2 of I plus 1, where I is basically your index where it is. Okay, so and it is a summation from I is equal to 1 to K. Okay, so for this the score would be 2 because this relevant score is 2 by where it is. It is at the first position, so log of 2 plus then comes 1 by log of 3, then comes 3 by log of 4, then comes 0. So let's say the score comes out to be 0.6. Okay, now what does this IDCG mean? IDCG means what should have happened ideally. Ideally, what should have happened? 3 should be at the top, then 2 should be there. So basically the order of the video should be A, then B, then C, then D. The score should be 3, 2, 1, 0. And if if I do the calculation, then it should be like log of 3 by 2 plus 2 by log of, what do we say, 3 plus 1 by log of 4 plus 0 by log of 5, right? Let's say this quantity comes out to be 0.9. Okay, now when we divide these quantities, 0.6 by 0.9, let's say the quantity comes out to be 0.5. Let's say. So what does this mean? This means that my model is according to the ideal behavior. This much percent of 50% of the behavior it shows according to the ideal model. So this is bad. If it is shows something like 80% to 85% or 90% of the ideal model behavior, then it's good. Okay, so this is one of the metrics that is used for measuring the ranking quality. Okay, and then there is another metric that we can use, that is mean reciprocal rank. So what does this mean reciprocal rank tells us? This mean reciprocal rank tells us that, hey, how fast did my model show the most relevant video? So let's say you searched a video, you searched a topic, let's say cute dog videos. Okay, and it showed 3 videos to you, let's say 4 videos. On this there was something related to cats. Here it was related to Punjabi song, and here it was related to a cute dog. So you see, it is at 3rd position. So this measures that how fast my model was able to show a relevant video. So if it is showing at 3rd position, it means it's bad. Now what is the formula for it? So the formula is 1 by m summation 1 by the rank where the relevant video came. So let's say we run this 4 times. Okay, and the first time the relevant video comes at 2, then it comes at 1, then it comes at 3, and then it comes at 4. So 1 by 4 into 1 by 2 into 1 by 1 into 1 by 3 into 1 by 4. That is how you calculate the mean reciprocal rank. Okay, so these are the 2 matrices, and the most important matrix, that is NDCG @K. That is generally used for offline evaluation. Now coming to the last part, that how are we going to exactly serve it to the end users? Okay, see, to answer this question, we will divide this into 4 categories. What we will pre-compute. See, there are 10 million videos. You won't do anything. If you try doing everything online, then it will take a lot of time complexity, right? It would take a lot of time to show relevant videos to the user. So what we will pre-compute. Second is what happens when the user queries. Third question is that, hey, how do we retrieve? Fourth question is that, how do we show it to the users? How do we show it to the users? If you answer these 4 questions, then the whole serving part gets over. See how we are going to answer that. What we will pre-compute. See, we have 10 million videos, right? We have already trained our model. Now, do you think, let's say, if a video is coming, do we need to every time, let's say if I have 10 videos, do I need to make sure that I pass that video always in my model to show it to the end user? No, right? We can save their embedding somewhere. So how we are going to do that? See, we have 10 million videos. We have a trained model. We get the video embeddings out of it. How we get the video embeddings out of it? You know how? So we have something like this. 1 second. You had this final video embedding. How did you get the final video embedding? That is multiplying it to the projection layer, and you get a final video embedding, right? This is the thing that you save. But where do we save? That is a question. So we are going to save the embeddings in a service which is like a ANN service, approximate nearest neighbor service. So this kind of a data structure that will help you store the embeddings in such a way that if you want to know that what embeddings are near to each other, you can easily calculate that. Okay. Now, these are the embeddings that we are going to store. 10 million embeddings. This is pre-computed, stored somewhere. Okay. And we have some service attached to it, that is ANN service, which helps me. Let's say if I send a embedding to it. Let's say if I send a embedding 0.1, 0.2, 0.3. This is the embedding example of. If I say that what embeddings are closer to each other, tell me the 500 embeddings. It will give me the answer in like 50 milliseconds or 100 milliseconds max. This will use some algorithms and will give me this. Okay. What algorithm it will use is, again, like I don't want to cover that in this video. You can just say that it's just a ANN service, that what it's going to use is that it's going to get you the top 50 embeddings which are closer to this particular embedding. Okay. And we are going to save these embeddings. So we have pre-computed them and saved it somewhere. What happens when the user queries? User query, it's just a text. I pass it to a pre-trained model, that is BERT or something like that. And then I pass it to the train WQ. You remember I told you that there is a trainable projection layer. It gives me the final text embedding. So the answer for this is what happens when the user queries. It gets converted into a final text embedding, final query embedding. Okay, this is the second thing. Third is, how do we retrieve? The answer is ANN. We pass it to this text embedding. Okay, this text embedding, and say, bring me 500 video embeddings which are closer to this text embedding, right? Because we know that video embeddings which are closer to each other, which are similar to each other, will be closer, right? And the work of this service is to bring all such embeddings. How it will bring? It will tell that, okay, video ID V1 has this embedding, video number 547 has this embedding, video number 223 has this embedding, and these embeddings are the top embeddings which are closer to this text embedding. Okay. Coming to the fourth part. This is the answer to the third part. Coming to the fourth part. How do we show it to the users? See, you got the scores, but still you did not do a dot product now. You need to perform a dot product between what? The textual embedding and the video embeddings that you got. Let's say you perform the dot product. The scores are 0.98, 0.97, 0.96, all that. Out of this, you get the top 200 scores. Top 200 scores. What you are going to do that? Sort them. You have sorted all of them. Now what you are going to do? The simplest thing which every production system does is, it has a re-ranking service. Now what does this re-ranking service even mean? See, what happens generally is that we need to apply some business logics. So for example, all the videos that I'm showing are related to, let's say there is a video which has like cute dog plus something like which is hilarious, right? Or is it is by some new content creator, right? So we need to push it to show it at the top. So we apply some business logics to make sure that it comes at the top, or it comes at 4th or 5th position, right? So such kind of logics are applied at the re-ranking service. It's pure business objective logic that we are applying here. So here is no ML stuff that is working here. ML works till here only. After that, it's re-ranking services, your business logic that you are applying to the scores that you are getting. Okay, so so this is how exactly the end service will look like. Hope I was able to explain you the whole YouTube video search part. Thank you.